we are discussing optical sources for communication. In the last lecture, we described the characteristics which we are looking for in an optical source, and then we found that the sources which are semiconductor based, they are most suitable for optical communication, because these sources, they are compatible with optical fiber, and at the same time they are also compatible with the electronics. Then we saw that in a semiconductor source, you can have what is called light emitting diode or LEDs or the injection laser diodes, and then we started discussing the basic principles of light emitting diode. The basic idea there was to see, if we take a semiconducting material, what kind of radiation we get from a semiconducting material, that is, what are the spectral characteristics of the radiation which we receive from a semiconducting material, and then what is the efficiency with which the radiation can be emitted from a semiconducting material. So, we took a simple semiconducting material, and then we had a very simple model which said that if you are having electrons and holes in conduction and valence bands respectively, then any electron can combine with any hole and can give you a corresponding photon out. At this point of time, we are assuming that every electron which is recombining with the hole is going to give a photon out. So, we are assuming that the efficiency is 100%, and then we ask a question that when the electrons and holes are distributed in the conduction and valence band, then what kind of spectral distribution we will get from a source. So, we took a very simple model, and then we said that the energy level diagram for a semiconducting material will be, there will be a conduction band here, there will be a valence band here, this is the energy band gap, and if you take an intrinsic material, then you have a Fermi level which is midway between the two, and then availability of an electron in the conduction band will depend upon two things, that is availability of a energy state which is given by this distribution of energy state function, and then occupancy of that energy state by an electron which is given by the Fermi function, which is this. Similarly, in the valence band, the availability of a hole will depend upon the available energy state in the valence band, which is again given by this energy density function, and then non-occupancy of that energy level, which is given by 1 minus this Fermi function. So, then by taking this simple model, that we wrote down essentially the probability of having a hole in the valence band in a p-type material, and then making certain approximations that the energy levels which you are talking about are much smaller compared to the Fermi energy level, we got the probability of a hole which was approximately given by this quantity. Similarly, we did the exercise for the n-type material, and then we said the probability of having an electron in the conduction band, that is approximately given by again this function, which is the exponential function. While doing this, if you recall, we had assumed that the variation of the density of energy states is assumed constant in the conduction and valence band, and that is with the understanding that this function is a very slowly varying function of energy. So, over a small range of energies where electrons and holes are primarily confined near the edges of the bands, the function can be assumed more or less constant. So, under these assumptions, essentially we got the probability of electrons in conduction band and probability of a hole in the valence band. And then we said, if you take a material now and make a junction out of it, which is a PN junction or nothing but a diode, and if you make this diode forward bias, then holes and electrons are injected in the depletion region, where the recombination between the electron and hole will take place, and every recombination will give a photon out. So, you will get a light which will be coming out of this. So, then saying that the photon is generated now, we are now asking what is the probability of a photon generation. Once we know the probability of electron in the conduction band in n-type material and probability of hole in the valence band in the p-type material. So, we said the probability of photon generation is proportional to the density of electrons as a function of energy level, and in conduction band we are representing energies by E2 multiplied by the probability of a hole in the valence band, and there the energy is represented by E1. So, substituting now for these two probabilities of electron and hole, we get the probability of photon generation, which will be essentially given by this. And then by separating out the terms, we get a term e to the power minus E2 minus E1 divided by kT multiplied by this quantity, which is a constant, because for a given doping of the junction, the EFN, which is the Fermi energy for the n-type material, and EFP, which is the Fermi energy for p-type material, are constant. So, this quantity is constant for a given device. So, then we see that the probability of photon generation is proportional to e to the power minus E2 minus E1 divided by kT, and K is the Boltzmann constant and T is the absolute temperature of the device. Now, if you look at again the energy diagram, we will see that we have a conduction band here and we have a valence band here, and now you are having holes which are distributed in this region, and then you are having electrons which are distributed in this. And as we said, any electron can recombine with any hole and can give me a photon out. So, essentially if I consider this electron and if I consider this hole, this recombination which is going to take place from here to here will give me a photon out. Similarly, if I consider a hole here and if I consider electron here, this difference between these two energies is exactly same as this difference. So, this also will give me a photon out, and this photon will have a same energy as the energy of this photon. And as we saw, the energy of the photon is proportional to the frequency of the photon. So, frequency of these photons will be same. So, now if you want to find out what is the spectral density of the emission from this p-n junction or from this semiconducting material, then essentially we have to add up all the electron hole pairs which have a energy difference same as the photon energy in which we are interested. So, what that means is that this quantity here now E2 minus E1 is nothing but the photon energy or the frequency of the photon which we are looking for. So, this quantity E2 minus E1 essentially is constant, but then we are having all possible pairs which we have to now add to find the total number of photons which are going to be generated. Or in other words, essentially we have to integrate this quantity for all possible energies for which this difference E2 minus E1 is equal to energy of the photon EPH. So, what essentially we are saying is all electrons starting from here and for which the corresponding hole will lie somewhere here, we can go all the way up till this hole will lie on this edge, and then you will have corresponding electron here. So, if I integrate, this is the energy which is EC, this is the energy which is EV, and the energies in the conduction band is given by E2. So, if I integrate this quantity here for all values of E2 going from EC to EV plus the photon energy in which we are interested in, then we will get the total number of photons which will be emitted for a given frequency or for a given energy. So, while integrating this, essentially we are doing as follows. We are finding out now the total number of photons that is proportional to integral, and if you are integrating for E2, then as we said, this goes from EC to EV plus E photon, which is EPH. We are integrating this quantity. There is a constant here which goes into this proportionality constant. So, this is e to the power minus E2 minus E1, which is EPH divided by KT. We are integrating with E2. So, this quantity is constant, which we can take out. So, essentially the total number of photons emitted at a given frequency or at a given energy, which is E photon, are essentially given by EV plus EPH minus EC minus e to the power minus EPH divided by KT. Now, this quantity here EC minus EV we can put as the band gap, which is EG. So, essentially we get the total number of photons that will be proportional to the quantity which is EPH minus EG, the band gap energy, e to the power minus EPH divided by KT. So, firstly, the model which we have discussed here is valid for the energies which are more than the band gap, which is EG. So, if the energy is less than the band gap energy, then there is no possibility of recombination. So, the model is not valid because the photon is not going to be emitted. So, essentially this number of photons which you are calculating, this is only true for the energies which are greater than EG. So, now if I look at this quantity here, you will see that initially when EPH is equal to EG, then this quantity is 0. So, there are no photons emitted for the energy which is equal to the band gap energy. As EPH increases, this quantity increases, and this quantity is still very small because EPH is a small quantity. Then after some time the exponential function starts dominating, and then again the function starts decreasing. So, you have a sort of a local maximum for this function at which the number of photons will be maximum. In fact, you can just add one term here minus EG, which is a constant quantity for a given material. So, you can write down this quantity here as EPH minus EG e to the power minus EPH minus EG divided by KT, and e to the power plus EG you can multiply, and since EG is constant for a given material, that can again be absorbed into this proportionality constant. So, if I now plot this function, that is number of photons as a function of the photon energy, and that essentially gives me the spectral distribution of light emitting diode, then we get a typical curve which will look like that. Now, as I mentioned, when the photon energy is equal to EG, then the power or the number of photons which are emitted is 0. As the energy increases, photon energy increases, the number of photons increase or the power increases. It reaches to the maximum when photon energy is Eg plus kT, and then again it starts decreasing exponentially, and for large photon energy the power is practically 0. So, we get a spectral distribution which looks a asymmetric kind of distribution. The maximum power is received not corresponding to the energy which is the band gap, but is little more than that. Of course, this quantity kT is a very small number compared to Eg. Typically, the band gap energy for semiconducting material is of the order of about 1 eV, whereas this quantity kT will be of the order of about 0.025 eV at room temperature. So, this quantity is very small compared to Eg. Nevertheless, the maximum power is not received for energies equal to the band gap energy, but for the energy which is a little higher than the band gap energy. The second important aspect, however, for this analysis is that this quantity here, if I measure the effective width of this function, that gives me the spectral width of the light emitted by the LED. And if I see approximately, if I take this function and find out the width of this function, you will see that this width is approximately 2 kT. So, when we go from one semiconducting material to another, this quantity Eg changes, but as far as the width of the spectrum is concerned, that is 2 kT and has nothing to do with the band gap energy Eg. Or in other words, when I go from one semiconducting material to another material, the peak wavelength or peak frequency would change because Eg would change, but the spectral width is independent of the material. As long as the material is having a temperature which is T, the spectral width is 2 kT in energy. And this is not a very good feature, because what this means is that the spectral width, which is one of the very crucial parameters for optical communication, is not in our control at all. So, if we use a light emitting diode as a source for optical communication, then spectral width is decided purely by the operating conditions, which is equal to 2 kT. In the presence of impurities in the material, this may range over a range of 1.5 kT to about 3.5 kT. But again, the thing to note here is that this number is independent of Eg. So, depending upon the operating conditions, you may have a spectral width, and this spectral width will be independent of the material or the wavelength at which the emission is taking place. So, now I can ask quantitatively, having understood this, what is the spectral width which the LED typically has when the LED is operating at 850 nanometer or 1310 nanometer or 1550 nanometer. So, we know the relation that the lambda is equal to Hc divided by E photon. We are looking here for the spectral width, that means the change in the wavelength. So, we can take delta lambda, that is equal to, I can differentiate this with respect to EPH. So, I get minus Hc upon EPH square into delta EPH. So, this is the spread in the energy of the photon from the spectrum. This is the corresponding change or the spread in the wavelength which we will get in the spectrum. We can take Hc upon EPH, which is nothing but lambda. So, we can take this quantity lambda and bring it down. So, you get delta lambda upon lambda, all the relative spectral width for the source, that is delta EPH divided by EPH. Now, delta EPH, as we saw, is approximately 2 kT, and this is the photon energy. If you substitute that, then you get now the relative spectral width of a source, and this is essentially tabulated here. So, we have got a lambda, which is the operating wavelength of the LED. This is the spectral width delta lambda, and this is the quantity delta lambda by lambda, which essentially gives me the percentage spectral width. So, if I take a semiconducting material for which the band gap corresponds to 850 nanometer, which is gallium arsenide, then we will have a spectral width approximately about 30 nanometer or 3.6%. Whereas, if I go to other ternary or quaternary materials for which the spectral width is 70 nanometer and emission wavelength is 10 nanometer, the percentage spectral width is about 5.5%. And if I go to the third window of emission, which is 1550 nanometer, then the spectral width will be as large as 100 nanometer, or the relative spectral width will be 6.5%. Now, remember, when we were discussing different windows for optical communication, we went from 850 nanometer to 1310 nanometer, because that is where the dispersion is going to be lesser. But that was under the assumption that other parameters of the system remain same. What we find in this case now is that as you go to longer and longer wavelengths, the spectral width of the source increases, and therefore, the dispersion in the optical system increases. So, dispersion for 1550 nanometer will be almost 3 times compared to what dispersion you will get at 850 nanometer. So, LED has one of the major problems, and that is it has a very large spectral width, and that is the reason if you use LED as a source for optical communication, then the data rate is very small. It could be only of the order of about tens of megahertz or maybe 100 megahertz, but beyond that the dispersion will be unmanageable, because the spectral width for this source will be very large. The second issue which is there for LED, well, before that let us look at this LED spectrum again, which is this. And as you note here that the LED spectrum, what we have calculated theoretically, looks highly asymmetric. It has a very rapid cutoff at Eg, and this tail extends very smoothly on the higher energy side. Whereas, if you take a typical LED spectrum in practice, you will realize that the spectrum does not look that asymmetric. The spectrum look more or less symmetric. So, if I take a typical LED and if I look at the spectral distribution of a typical LED, it will look something like that. This does not have a very rapid cutoff on one side and tail extending on the other side. And this has something to do with the practical conditions of LED, and that is when we talked about the energy level diagram, we said there is no electron hole recombination possible because there are no energy levels present between the forbidden band. Whereas, in the presence of impurities, one will see that there are certain energy levels which may also exist within the forbidden band. So, there is a possibility of recombination even for the energy differences which are less than Eg. So, you will get some light for the energy of the photons which will be less than Eg, which theoretically we said that there is sharp cutoff at Eg because there is no recombination possible for the energies less than Eg. Second thing what will happen is that if the electron is here at a very high energy compared to EC, and if the energy level is available here within the conduction band itself, then the electron may jump from here to here and can shed away certain energy. So, as the recombination of these electrons around the peak takes place with the holes, the higher energy electrons can jump down to fill those energy states. Or in other words, the electron hole pairs which have a very large energy difference, they will be depleted. So, you will have a less photons corresponding to the very high photon energies, and you will have little higher photons for the energies which are less than band gap energy. So, the distribution which we have got here, it says that this function dies down little more rapidly, it does not extend that smoothly for a very long energies. Similarly, you have a function, now there is some photon can be emitted even in this region. So, this function extends little something like this, and this function dies down little more rapidly. As a result, we get the spectrum which looks more symmetric spectrum, and this is what is shown here. So, in practice, if you look at LED, it does not have an asymmetric spectral distribution which we have got theoretically, but it has much more symmetric distribution in terms of frequency or wavelength. The second aspect of the emission from semiconducting material is the efficiency issue. We saw that when the electron hole recombination takes place, there are two processes which are there. One is what is called the non-radiative recombination process, and other one is the radiative recombination process. And we have seen that when the electron hole recombination takes place, the photon may be emitted or the photon may not be emitted. If the photon is emitted, then that radiative recombination process is the useful process, because we got light out. But when the electron hole recombination takes place, and if the energy has gone in some other form like lattice vibration or something like that, then the photon is not emitted and the light has not come out. So, when we create a p-n junction and when the electron and holes are injected into the depletion region, the recombination takes place, but for every recombination we may not get a photon out, and that is the quantity is captured by what is called the quantum efficiency. So, what we have seen, we have got for the recombination two processes, the radiative recombination process and the non-radiative recombination process, and for emission of light, this is the process which is the responsible process, and this process is essentially is a vestige of recombination, because this recombination does not give any photon out. So, then one can define now quantitatively what is called the quantum efficiency, which is conversion of the electrical energy to photons. Now, generally the quantum efficiency is divided into two parts. One is what is called the internal quantum efficiency, which has something to do with the photon generation process. The second quantity is what is called the external quantum efficiency, which is something to do with the capturing of the photon which is generated. So, I can define now these quantities, the internal quantum efficiency and the external quantum efficiencies are as follows. The internal quantum efficiency is the total number of photons generated inside the device divided by the total electron hole recombinations, or in other words, internal quantum efficiency is a ratio of radiative recombination to total recombinations. And this process has something to do with the intrinsically with the material, the impurity level, and so on and so on. So, you will see that the internal quantum efficiency will be decided by the intrinsic properties of the material and maybe the fabrication process. The external quantum efficiency, which has something to do with the collection of the photon, that is defined as the number of photons guided to the fiber divided by the total number of photons generated. So, the photons are generated, but what process the photon has to go through till it becomes finally available for communication or reaches inside the optical fiber, that quantity is given by this external quantum efficiency. So, total efficiency will be essentially the product of these two, the internal quantum efficiency and the external quantum efficiency. So, let us see now what are the factors which are responsible for this efficiency. Firstly, when you are having a region and in which some carriers are injected, and let us say some n carriers are injected inside this, the rate of change of recombination or disappearance of this carrier would be proportional to the carrier density. So, we can write the equation that is dN by dt minus, which says that because of the recombination the carrier density is reducing as a function of time, that is proportional to the carrier density n. Now, this is a very simple equation, we can solve this equation and we get the n as a function of time, that will be equal to the initial injected carrier density e to the power minus t divided by tau, where tau is called the lifetime of this injected carrier against recombination. So, this quantity is the lifetime of carrier. So, essentially the recombination process now can be characterized by this parameter tau, which is the lifetime of a carrier against recombination. From here we can also see that dN by dt minus, that is equal to n by tau. Now, we have seen that there are two processes which are responsible for this recombination. So, each process now can be characterized by the corresponding lifetime against recombination. So, we have a radiative process and we say the lifetime against recombination against the radiative process is denoted by the lifetime tau RR, whereas if the recombination is non-radiative, then the parameter tau is denoted by tau and R. So, we have tau RR, which is lifetime against radiative process, recombination. Similarly, we can say tau and R is lifetime against non-radiative process. So, if both the processes are acting simultaneously, then the depletion of the carriers injected in a region will be the disappearance due to the radiative process and due to the non-radiative process. So, if I say that the total recombination which is going to take place is characterized by the total lifetime, then we can say that the n upon tau will be equal to n upon tau RR plus n upon tau NR. So, rate of recombination, total rate of recombination is equal to sum of the recombinations due to radiative process and sum of the recombination due to the non-radiative process. So, we can say here now that the total rate of recombination that is minus dN by dt, that is equal to, or just say this is total, that is equal to minus dN by dt due to radiative process minus dN by dt due to non-radiative process. And as we saw here, minus dN by dt is equal to n upon tau. So, you can substitute here. So, we say this is n upon tau, where tau is the total effective lifetime of the carrier, that is equal to n upon tau RR plus n upon tau NR. N is common. So, essentially we get 1 upon tau, that is equal to 1 upon tau RR plus 1 upon tau NR. So, what that means is that the effective lifetime will be decided by smaller of the two. If the tau RR is much smaller compared to tau NR, then the effective lifetime will be same as tau RR. Whereas, if tau NR is much smaller than tau RR, then effective lifetime will be more or less as tau NR. So, smaller of the two essentially will decide what is the effective recombination lifetime of the carriers when they are injected in the depletion region. Once we get this, then now I can talk about the internal quantum efficiency, and that we saw that is equal to total number of photon generated. So, this quantity is nothing but the rate of radiative recombination divided by the total electron hole recombination. So, that is the total rate of recombination. So, from here we get now internal quantum efficiency, which is internal, that is equal to minus dN by dt radiative divided by minus dN by dt total. Substituting now for dN by dt radiative and total, we get this is equal to n divided by tau RR divided by n divided by tau. So, which is equal to n divided by tau RR divided by n by tau RR plus n by tau NR. So, we get internal quantum efficiency, that is equal to 1 upon, all the n will cancel, we can divide by tau RR, you get 1 plus tau RR by tau NR. So, what we see from here is that if tau RR is much smaller compared to tau NR, then this quantity is negligibly small and internal quantum efficiency is almost equal to 1. So, we say that if tau RR is much less than tau NR. That gives me the internal quantum efficiency almost 1. But if tau RR becomes comparable to tau NR or larger than this, then the efficiency drops very rapidly. What that physically means is that when both the processes are operative and when the electron holes are injected for recombination, if tau RR is much smaller compared to tau NR, before the electron holes can recombine against the non-radiative process, they have already recombined because of radiative process and photon is emitted. So now the non-radiative process does not have a chance to show its effect, because before it starts showing its effect, the electron holes are already recombined and the photon has been emitted. So what we want for good internal quantum efficiency, this quantity radiative recombination should be much smaller compared to the non-radiative recombination lifetime. However, what happens is that this quantity, which is tau RR, is intrinsic parameter of the material used for making this device, whereas this quantity tau NR depends upon various factors. It depends upon the impurities, the energy levels which are created, the artifacts where recombination can take place. So this quantity is the one which depends upon fabrication process, the impurity levels and various things, whereas this is the quantity which is an intrinsic parameter of the material. So if I consider gallium arsenide, then tau RR for this is of the order of about 100 nanosecond. And if I consider the tau NR will depend upon the impurity level, and if you take very pure material, then tau NR will be very large, and most of the recombination would take place because of radiative recombination and you will get efficiency. But in practice, tau NR also is of the order of about 100 nanosecond. So due to impurities, tau NR is also of the order of about 100 nanosecond. As a result, you get the internal quantum efficiency of the order of about 0.5. That means whatever electron hole pairs are recombining, approximately 50% of that give you photon out. And this number is not too bad a number, for a simple reason that whenever we talk about a conversion of energies, anything which is more than about 20-30% is considered to be a good efficiency. So from that angle, conversion of the electrical energy, which is in the form of electron hole pairs, into an optical energy, which is a photon, is a fairly efficient process, because 50% of these recombinations give you a photon out. The second efficiency, which is external quantum efficiency, that is the one probably which is much more problematic, and that depends upon various factors. So here we are saying that the external quantum efficiency, which is number of photons now guided to the fiber divided by the total number of photons generated. So here photon is generated now. Only thing, now we are trying to get this photon finally guided inside the optical fiber. So let us look at the journey of the photon after it is emitted. So let us see, we are having a semiconducting material here where the photon is generated. Now note here, when the recombination is taking place, the recombination is not taking place on the surface of the semiconducting material. The recombination will take place somewhere deep inside this material, somewhere here, and a photon is born here at this location. Now, since the photon is born and it does not have any history, and photon is nothing but a packet of light, it starts moving with velocity of light. But since it does not have any history, it does not know which direction it should go definitely. So, there is a equal probability of a photon which is generated because of this recombination to travel in different directions. Or what it means in other words is that as soon as the photon is born, it is scattered with equal probability in all directions. So, now we are saying that when the photon is born here, it can either go this way, or it can go this way, or it can go this way, or it can go this way, this way, this way, and so on. Now, note here that the semiconducting material typically has a refractive index which is quite high. So, let us say the refractive index for this was Ns, and the refractive index here is let us say N of A, and typically Ns is greater than Na. So, the photon essentially is trying to go from a denser medium to a rarer medium, and as a result there may be a possibility that when it is incident on this interface at an angle which is greater than the critical angle, the photon is reflected back inside the material again. So, what is happening is that the photon which is going like this will come out, the photon which is going this way will get reflected like this, the photon which goes like this, maybe if this angle is equal to the critical angle, it will start moving like this. But if the angle is more than this angle, then the photon will be reflected back inside the semiconducting material. So, what we are saying is, although the photon generation is isotropic, that means there is the equal probability of photon emitted in all directions when at the point of generation of photon, the photon which can escape out will correspond to a cone, this cone, which is 2 times the critical angle, 2 times theta c. So, we can calculate what is the angle which is theta c, because we know the refractive index of the material, we know the refractive index outside. So, theta c will be equal to sine inverse of Na upon Ns and if I consider a material like gallium arsenide, this quantity is 3.6, and if I say that the photon is getting emitted in air, this is Na is equal to 1. So, you have for gallium arsenide theta c is approximately equal to sine inverse of 1 upon 3.6. So, if I take approximately this quantity, let us say 4, so 1 upon 4. So, theta c will be of the order of about 15 degrees. If I take accurately, it will be about 18 to 20 degrees. So, what that means is that although the photons are born with spherical symmetry, only photon which are lying within a cone of only plus minus 20 degrees from this direction can escape out. All other photon essentially will get reflected back inside the device, and ultimately they will again give the energy to the carriers, and the energy will get thermalized. So, essentially what we are saying is the fraction of the total number of photon which were born, which can escape from here or which lies within this solid angle corresponding to this 2 theta c, that is the one factor affecting the external quantum efficiency. And if I just do a simple calculation to find out what fraction will come out of this, so I calculate solid angle corresponding to this and divide by total 4 pi solid angle, I will get the eta external 1 due to this total internal reflection, that is equal to Na square divided by 2 Ns square. And approximately again for gallium arsenide, if I substitute these numbers, it will turn out to be 0.036. So, it is interesting now to note that if 100 photons were born here inside the material like gallium arsenide, only about 3.6 photons on average would be capable of coming out of this device, or there is a loss of 96 photons. So, major efficiency loss takes place right here in escaping the photon from the device. So, photon generation process is a very effective process, but capturing the photon and bringing it out of the device and guiding it inside the optical fiber is probably far more difficult process. So, we will continue with this discussion. We will see that there are many factors which will now contribute to ultimately capturing the photon and guiding into optical fiber, but just from the viewpoint of taking the photon out of device, you will see that we have an efficiency which is hardly about 4%. So, the external quantum efficiency is much more important parameters for a device than the internal quantum efficiency, because internal quantum efficiency is 50%, but capturing the photon is more difficult, and therefore, external quantum efficiency is much smaller compared to the internal quantum efficiency. So, in the next lecture, we will see other factors which will contribute to the external quantum efficiency.